So moving forward, some of the modern latest IT trends that we have seen over the last few years from left to right, if you see on the screen, there's a lot of digital transformation going on, a lot of monolithic applications or old legacy applications are now being transformed into smaller microservices-based architecture or modern applications so that they can benefit modern use cases. There is a lot of AI ML use cases around. There are a lot of edge computing use cases around. We have sensors feeding data. We have different types of sources producing data which require real-time, processing and handling of the data. And then, a lot of large organizations are moving towards cloud. Some of them, a lot of them are moving towards multi-cloud. Some of them are moving towards hybrid cloud, where part of infrastructure runs on-prem, and part of infrastructure runs in the cloud, and so on. And all this drives to the way application architecture has changed over the past few years. Like I said earlier, an example would be breaking a large monolithic application suite into smaller microservices-based architecture, and so on. And all this has resulted in rising customer expectations. And if you look at the screen from right to left, I know the the data, the direction in which this particular page flows is from left to right. But in my opinion, it also makes sense if we view this, in a reverse direction, where we say that, hey, in today's time, in modern time, modern customers want modern things, which basically means they want ultra fast applications, highly responsive applications. Privacy has become really, really critical. We know how important securing your data. It has become, given in the modern times of hacking and a lot of hackers and a lot of break-ins happening these days. And all this comes with a critical, requirement of, having a stable infrastructure where customers can rely upon and depend upon, that their data is safe, their information is safe, and it is available as and when they need. So the modern customer expectations have driven have forced the developers and the architects to write their applications differently, and then that demand has resulted in all these strategic IT trends that you see on the left-hand side. Modern application, modern architecture, make use of hybrid cloud, make use of modern infrastructure, makes use of AI ML use cases, and so on. So I skipped that part. So where does Hazelcast fit in? Traditionally, if you focus on the left-hand side of the screen for a minute, traditionally, the legacy applications, the old applications, they were reliant, they were dependent on the databases for accessing their data. Right? They would store data in disk-bound databases, RDBMS, and so on, and they would retrieve data from the databases. A lot of use cases would run stored procedures, databases bound computing, and all those things. But a critical problem, the single most important problem with doing anything or everything with database is that databases have been disk bound. They are still disk bound technologies, right? Most of these databases these days today, they offer the in-memory layer or the in-memory aspect of it, but it's not. But major part of it had been, disk bound, and anything which is disk bound is going to give you, is not going to be as fast as the modern demands, modern applications demand them to be, and that is where Hazelcast comes in. So if you look at the center of the screen, digital stack, which is where new applications are being written, new architectures are being drawn, and which basically which work on the premises of having an ultra fast access to the data, which is where Hazelcast comes in. Now, Hazelcast is purely in-memory technology, where it offers you the capability to store data in the memory and read data from the memory part of things. Now, reading data from the memory makes the whole thing super fast, gives applications the speed they need to cater to their customers' requirements of highly responsive, high response times. So low response times and highly responsive applications. And all this while, if you notice, the size of the database has shrunk from traditional stack into digital stack. So some may ask, does it mean that Hazelcast is a replacement of database? So the answer is not always. There are still, I would say, there are many customers, still many customers and many users out there who use Hazelcast, but also run database behind Hazelcast. And they run database because Hazelcast provides the tools and means to store the in-memory data into database and read data from the database if the data in Hazelcast is not found. So applications have access to the data all the time, no matter where the data is stored, whether in memory or on the disk or on database, and Hazelcast runs on top of the database. But the most commonly used data is now kept in Hazelcast in the in-memory layer, which is why you see the size of the database has now shrunk down to a smaller bit. And the dependency on Hazelcast has increased. More data goes into Hazelcast. We're talking about terabyte scale, which is why you see the size of Hazelcast bit in this architecture has increased a lot. And then the next bit is the infrastructure, where from hypervisor-based VMs and on-prem machines, we are now talking about container-based containers running on OS, on VMs, and serverless programming, and that's where Hazelcast fits in nicely. And I'll talk about that in more detail later on. The benefits of using Hazelcast, like I said, it's in memory. So whatever you do with data stored in Hazelcast, you do that at ultra low latencies, which basically means extremely fast access to the data, resulting in high throughput. So what those two terms mean, that you now have fast access to data, so you are able to perform an operation faster than you would have done, or you would have been doing with databases. And when you are able to perform an operation, a complete operation faster, then that basically results in the ability to serve a lot many more users at any given point in time. So basically high throughput. And Hazelcast also provides the ability to perform the processing of the data, which might be running in the streams, infinitely and constantly flowing stream, or the data might be stored statically somewhere, and you want to process that. And all that I'll talk about in a minute in more detail. And the major I would say differentiating factor between Hazelcast and its competing technology is that the ease of deployment. Those who have used Hazelcast before would know that using Hazelcast is as easy as downloading a simple jar file, which is basically in the region of 15 to 20 megabytes, putting in the class path and start using API. And just with that, you can spin up a 100-node cluster easily in no time. And the last but not the least, it is totally cloud native and cloud compatible. And I'll give you a demo at the end where I'll show you how Hazelcast can be run in multi-cloud and hybrid cloud environment. Moving forward, so Hazelcast, you probably, those who are aware of Hazelcast and those who are not, traditionally, Hazelcast had been an in-memory caching or distributed caching technology, where when we started our life about 10 years ago, we started as a simple in-memory distributed data grid, where we provided the ability to store data in the memory of Hazelcast servers. And then a few years later, we added one more product, which is called Jet, and that provides the capability to perform stream processing and batch processing of the data within ultra low latencies and high throughput environment. And together, these two technologies form the platform. So over the next few months, you will hear more about Hazelcast platform being a unified view of both Hazelcast technologies. So today we have IMDG and Jet, But later in this year, when we release our platform, you will have one Hazelcast platform where you will be able to choose and use whatever you want, whether you want to use caching or jet or processing or both. You will have that option. And in my demo later in the session today, I will be giving a view of the platform itself later on. All right. So what you see on the screen is the complete architecture of Hazelcast compute platform, which has two aspects to it. One is IMDG, which is the data layer, which is the caching layer where the data is stored in the distributed form across the server nodes in the cluster in Hazelcast platform. And then the other bit is Hazelcast Jet, which is the compute aspect. Caching is simple. You put data in the memory of Hazelcast servers and you read data out of it. Now, when we look at caching in the context of platform, that's where things become interesting. So with Jet, you get the ability to perform, processing on the or to process the data, which might be flowing into an infinite and constant stream coming in from different types of sources. And then you want to, run your processing logic or you do some processing or execution on it. So if you look at the left-hand side of the screen, this is where the data comes into the system, what comes into the platform. Um, so the platform is able to ingest data from different types of sources. There is absolutely no restriction on the type of sources a platform can use. And it's not limited to what you see on the list on the left-hand side. So, but what you see on the list is basically currently we have the connectors available out of the box off the shelf. So the platform is able to ingest data from MQ messaging or Kafka, IoT sensors, databases, Hadoop-based databases, or direct socket connections with other applications and so on. And once the data arrives into the system, then you have the freedom of working with that data. Where once the data has arrived, you may either want to store the data directly into the cache, or you may want to perform some transformation operation on that data and run some analytics on that data before you store that into the cache. And when you perform any operations on that data, whether you are transforming or running analytics or aggregation and so on, during that processing, you may want to use some reference data or some static historical data. Let's say a payment transaction comes into my system. You swipe your credit card. That transaction, when you swipe a credit card at a credit card terminal, the transaction is taken to the backend server, and the backend system puts the transaction, let's say on a Kafka topic, where the Kafka topic brings the transaction into Hazelcast platform, which is where the entire processing logic will be executed on that transaction, which includes business checks, fraud detection rules, and all those things. Now, during that fraud detection check or the transaction processing logic, you first want to perform some transformation operation by adding some data into that onto that transaction, onto that transaction object or the data that is arriving in the system. And that reference data, that stack data might be stored in your cache. So compute side of things compute side of things have direct access to the data stored in the cache. So they pull the data from the in-memory layer of Hazelcast into the compute process, apply the data onto the compute, and then move on. And the moving on entails the next stages, which basically means running business checks, running fraud detection analysis, and running some aggregation on it. And once they are done with their processing, they can put the data back into the cache and publish the output. So from left-hand side towards the right-hand side, once the processing has been completed on the transaction and it has been decided whether the transaction is a go-ahead, is okay to proceed, or is a fraud transaction, we cannot allow the transaction to proceed. Whatever may be the output, that output is put onto an output channel, which is on the right-hand side of the screen. Just move this here, which is on the right-hand side of the screen. So again, there is no restriction on the type of output channels that you can connect to your Hazelcast platform. It is just an example, and from the view that these connectors are available off the shelf. Now, all this while, um, as you can see at the bottom of the screen, there is database connected to it, which is also showed as system of record, and then there is data lake and data science platform. And I'll come to that in a minute. So Hazelcast, like I mentioned earlier, can run very well easily on top of a database, but Hazelcast becomes the fronting technology or data store or your compute store for your application. So the application never really talk to the database. They don't know whether database exists. So if the in this example, when the transaction comes into the system, and if that transaction has now need to be persisted into caching layer as well as into database layer, then that is also possible through Hazelcast. And I'll give you a demo of that as well later in the session today. Another thing that we have added in our compute platform is called machine learning inference. So, which is you see at the bottom right, remote and machine learning model. So, catering to AI and machine learning use cases where you have data scientists and they have their own tools. Some use TensorFlow, some use R, some use other technologies, and they train their machine learning models in those technologies. Now, one of the issue that existed for a long time was to how to execute those trained models. In order to execute those trained models, a problem used to be where we needed to port those models into the compatible language so that the execution platform can execute them. This is not the case anymore. So if you are a data scientist and you are training your data models in, let's say, Python, and you don't want to change, and you just want to execute your data model when they are ready, they're trained and ready, then we use Hazelcast. And Hazelcast has this concept of machine learning inference, where it controls the entire data flow of your application execution, and it has the ability to basically invoke your machine learning models running in Python. So you never have to port, you don't really have to port your existing code into Java or into Hazelcast compatible code. It's not the case anymore. So you keep your data model, machine learning models running in the system where they are running at the moment currently, and you just let Hazelcast invoke those data models as and when Hazelcast needs them. So these are some of the latest and greatest things we have done, with regards to the technology. To give you an idea about what kind of user base do we have, and I'm not saying user base, but this is actually a customer base. Hazelcast started its life with banking and financial services. Actually, one of our first customers was Turkcell, based in Turkey. But then, we started increasing our presence in banks, within banking financial customers. Some of the, 50 of the Fortune 200 companies are Hazelcast clients. They use Hazelcast in one capacity or the other, and I'll talk about some of the use cases of some of those clients in a minute. And then we have large presence in retail, in consumer and e-commerce. As you can see, Apple and Target, some of our key customers, significant names. Good presence in telcos, AT&T, Ericsson, and so on. And then gaming, high tech, and insurance and public sectors. So all these guys, they use Hazelcast. Some of the top use cases from some of the prominent names that I picked up from that list. A common use case, and I also just talked about it, is payment processing. So Standard Chartered Bank, Visa, when you swipe your Visa credit card, or if you're making any payment transaction through Standard Chartered payment object, whether you're using Standard Chartered debit card or making online transaction or whatnot, or if you're a Deutsche Bank user and if you're making a transaction, all those payment transactions are now processed in Hazelcast. One of the key achievement at Visa for us was to defeat Redis fairly on performance. Those who are familiar with Redis, we did extensive POCs, and POVs, and it turned out that Hazelcast was 3 times faster than Redis. We could have gone more, we could have gone further, but we got bored at that point, and then we decided to, not bother about the Redis anymore. And then there are certain fundamental differences also that were very crucial to these customers in deciding which technologies to use. So payment processing is one use case. Then the highly, I would say a fast growing use case is mainframe optimization, where HSBC in London and National Australia Bank in Australia, they use Hazelcast to modernize their mainframe infrastructure, breaking legacy monolithic mainframe applications into smaller applications, making and modernizing them so that those applications can be used, for serving modern customer requirements. And another use case for modern mainframe optimization is to basically externalize the data. So Hazelcast has been a crucial, I would say, component in their journey of HSBC and National Australia Bank, in where they not only were able to reduce the cost of mainframe operations. So it is commonly known as MIPS. Those who are aware of or familiar with mainframe side of world, by keeping data in Hazelcast and avoiding hitting mainframes every time an application needed some data, and also making the data available to external applications, so that modern applications running outside of mainframe infrastructure can benefit the data which was previously stored in mainframe. So on both ends, it not only provided in-memory speed, but also the flexibility to externalize the data and making the infrastructure smaller so that it is faster to use and portable and so on. Another example is edge computing, where some of the key names, Sigma Stream is just one customer, but we have a lot of different deployments across the globe where Hazelcast is used in IoT space. One of the large cities in South Korea, it's called Daegu, and it's called a Daegu Smart City project, where Hazelcast is used in processing the data which is produced by sensors installed on each traffic junction, on public transport buses and trains and so on, and processing the data in real time. At Sigma Stream is basically a company that develops applications for energy companies, oil and gas industry. And in one of such deployment is where Hazelcast is deployed on an oil rig, where the rig has 10,000 different drill machines, which are constantly drilling into the seabed and extracting oil. And those drill machines operate under different parameters, with different parameters like their torque, their speed, the pressure applied on those drill machines, and the temperature and all those things. So, and those drill machines, they produce data in real time. Each drill has sensors attached to it, and they're producing data. They're producing data like, what is my current RPM, what is the current pressure applied in Newton metric ton, what is the temperature of the drill itself, and so on. And all these parameters are fed into a Hazelcast cluster, where Hazelcast consumes that data, does its calculation, and then provide a result, basically provide a result which basically defines how those drills will run. So if a drill is running at an RPM of 6,000 and it's been running for a while, and the temperature has, the temperature of the drill machine, the drill itself has reached 300 degrees Celsius, that may be a very high, number for a drill to operate on. So Hazelcast consumes the data produced by the drill, processes it, and then uses that data itself on the very same drill to say that, hey, okay, slow down. So that data is now used to control the very same drill itself. So the drill is now slowed down to 3000 RPM, and it is slowed down until the temperature comes into the acceptable region. So those are the kind of things Hazelcast is doing at Sigma Stream. And then some of the e-commerce use cases, where If you go to apple.com, you browse through the catalog, perform any transaction on the website. It all runs on Hazelcast. With Target, Target is a very large e-tailer, much like Flipkart and Amazon in India. Target is another e-tailer and retailer both in US, and they store the entire catalog, I think in the region of few terabytes, 3 or 4 terabytes in Hazelcast. And the story of Target is a bit interesting. I'm not gonna spend much time on that story. It's a long story. If you're interested, you can go to hazelcast.com and go into one of the resources and look for retail story of Hazelcast. But all that few terabytes of data can be browsed under 2 milliseconds of latency. That's how fast Hazelcast is. That's how fast access Hazelcast is able to provide to the applications, which is quite contrasting to the previous performance of the application, which was under 300, which was more than 300 milliseconds. Target's requirement was to bring that latency down to 40 milliseconds, which was their accepted SLAs, but Hazelcast was able to bring it down to 2 milliseconds, which is almost 300% improvement. And then Capital One started again, same thing, payment processing, fraud detection, all those things happen in Hazelcast. Now, these products that you see on the screen, some of them are open source projects, some of them are not. And I'm sure most of you have seen some of these applications and use some of these projects in your career, in your lifetime. And all of these guys, they use Hazelcast, in some capacity. So, for example, MapR, whenever you deployed a MapR cluster, it basically used Hazelcast underneath for clustering. Same goes with MuleSoft. If you deployed a MuleSoft architect cluster, it used Hazelcast for clustering. Same with Vertex and Twilio and so on. Very quickly, I didn't mean this to be part of the session, but since we are here, Hazelcast also formed a partnership with IBM a year and a half ago, where Hazelcast is now an accepted technology on all IBM cloud platforms, be it Cloud Pak for data, integration, automation, multi-cloud management, and so on. And also, it is the preferred data grid within the IBM, right? So IBM does not focus on selling IBM's own data grid called IBM Extreme Scale. They're now all of IBM sales staff or engineering staff, they now focus on using Hazelcast. All right, going into the use cases in more detail. Let's get this. You've seen this one. On caching, like I mentioned earlier, Hazelcast Hazelcast runs between your application systems and your databases. So business systems are your applications. They never ever talk to the database. They always talk to Hazelcast whether they are writing something, or whether they're writing some data or storing some data, or they're reading some data. They always interact with Hazelcast, and Hazelcast provides the means and infrastructure to work in tandem with RDBMS, so that all the data that is written by application into Hazelcast cluster can be now stored all the way into a database. There is no restriction on the type of database you can run. There is no restriction on the number of data stores you can run. We have customers who run Postgres and Cassandra together underneath Hazelcast. Any questions so far? No question? Okay. I'm still audible, right, Shavik? Vaibhav? Or am I talking to myself?
You're audible.
Yeah, okay, thanks.
2 questions on this.
Okay, cool. Moving forward, in the caching use case story, just a quick overview on how the data is stored in Hazelcast. Since we are talking about distributed technology, the data is also distributed. As you see on the screen, this is a 3 nodes cluster. This is just a reference for this session today. The data is stored in partitions, and the concept of partitioning is very similar to the concept of partitioning in concurrent hash map. As a matter of fact, Hazelcast is indeed an implementation of concurrent hash map. Um, so whatever data that you store or you want to store in Hazelcast is stored on these partitions. Hazelcast creates fixed number of partitions when the cluster starts, and those partitions are equally distributed across all the server nodes in the cluster. And whenever you store the data, that data goes onto one of those partitions. There are 2 types of partitions that Hazelcast creates. One is primary. As you see, there are A, B, and C. For A primaries, 4 blue primaries, 4 orange primaries, and 4 purple primaries. And then there is backup. So backup is basically the replica of your primary data store, of your primary partitions. And the backups are also distributed. Now the backups are created, and sorry, backup partitions are distributed in a way that they are not stored on the same JVM where the primary partition is. So if you notice, node A has 4 blue primary partitions and has the backup from 2 backup from B and 2 backup from C. Same goes with node B. Node B has 4 orange dots, and it has 2 backup of blue dots from A and 2 backup of purple dots from C. So the data of node C, the primary partition of node C, are backed up completely on B and A. And then same story for A, B, and the other 2 nodes. One of the important feature with Hazelcast is the flexibility. Flexibility to run or to manage a cluster based on your demand. So you may start a Hazelcast cluster with a certain number of nodes today based on your today's requirement, based on today's demand, today's traffic. But 6 months down the line, if your traffic increases, your business increases, that means more data to store in Hazelcast, which basically means added capacity. Then Hazelcast is flexible enough to allow you to increase the size of the cluster without affecting the availability of the cluster, without affecting the availability of the data. And how is that made possible? I'll show you in a minute. All these partitions, when they are created, they are assigned to their member nodes. So member is basically server. So each partition is owned by one of the servers in the cluster. So node A owns these 4 primary partitions, node B owns these 4 primary partitions, node C owns these 4 purple primary partitions. Now, whenever you add a node into the cluster, the ownership of these partitions change. And the way it changes, let's say in an example, I have 3 nodes cluster and I want to add node D, a 4th node to the cluster. So what happens is, Hazelcast, as soon as it sees a new node joining the cluster and it has cleared the security tests and all those things that it requires to do before it is allowed to join the cluster, then a process of migration starts. And the process of migration entails moving the existing partitions moving some partitions from existing nodes to the new nodes so that their partition distribution is equal. And that migration happens not just in primary space, but also in backup space. So backups are also moved across to the new node so that the partition distribution is equal and uniform across the cluster. So as you see, once the partitions have moved, my migration is completed and I have added capacity in my cluster. Right, so from 3 nodes, I have now scaled up to 4 nodes. And all this while, I did not require to perform any manual operation. Some of the existing technologies like Redis and others, they require you to run scripts and perform manual operations in order to, distribute the partitions or the data equally across the new nodes as well, and also perform manual operations to replicate the data onto the new node. Whereas in Hazelcast, it is all done automatically. And all this while my partitions were moving across the cluster was still performing. This was happening behind the scenes. But for the applications, they did not know that a node D, a new node, has joined the cluster. for them, the cluster was still operating at, at the normal procedure. So it did not affect the availability of the data which was already there in the cluster. Now, why do we have backups? So another aspect of flexibility is to deal with faults and failures. Any distributed technology can, but actually every technology, every software that you run, every infrastructure is prone to faults. Some are in our control, some are not in our control. So how Hazelcast handles faults. So let's say in that same 4-node cluster, node B crashed out, right? Node B, somebody either pulled the plug or somebody did, kill -9 or whatnot. Or node B was shut down because of maintenance reasons. So as soon as a node is confirmed to have left the cluster, and when I say confirmed, it is an important statement to make, because a node, before a node is decided to be out of the cluster, various things happen, so that it is conclusively decided that, okay, node B is actually out of the cluster, is not coming back. Because otherwise, what may happen, that one of the node may stop responding to its health checks and ping probes for a certain amount of time because of an intermittent network failure, and you don't want that node to be out of the cluster just because of a temporary network failure. So all those checks are conducted before a node is decided to be out of the cluster. Now, once a node is decided to be out of the cluster, then what happens? So node B had 3 orange partitions, primary partitions, which were stored backed up on node A, C, and D. Now, as soon as a node is detected to be out of the cluster, the backups are activated, right? And the data is restored from the backups. Now, what that means is that moving these partitions from backup space into primary space. And when I say space, since we are talking about the same JVM, the same server node, same memory space, we are not physically moving any partition from one place to another. All we are doing is changing the flag of a Java object, which is partition, and making it a primary instead of backup. And that's it. As soon as it is done, my cluster has recovered from a failure, and then the cluster creates new backups for the newly created primary data, and that happens behind the scenes for you. So even though I had a failure, I did not need to do anything at all manually. All that was taken care of by Hazelcast itself, and the cluster recovers from this failure by activating its backup, and my data is still intact. Right? I still have 12 partitions across 3 nodes now. Moving on to the computing side. So far we have seen caching of the data. Computing is into the world of JET. Now, JET is again, a distributed technology, totally and purely in memory. And it basically uses the same premise of distributed cluster formation of Hazelcast IMDG or Hazelcast caching side of things. JET is an implementation of DAG, which is directed acyclic graph. So those who are not familiar of what DAG is, what the hell DAG is, I suggest that you look it up. It's a very interesting topic. It gives you good insight into how modern architectures process the data flowing into a stream or continuously, infinitely, or perform batch operations. So with JET, it gives you the ability to process streaming data. So for example, you may have a source which is connected to the platform, and that source could be a Twitter feed, for example, where your platform is listening to all the tweets happening on a particular hashtag, and those tweets are happening in real time. Hundreds of thousands of users are tweeting on that. So for the latest example would have been India versus England test match just concluded in Ahmedabad. So all those tweets are going around, and all those tweets are happening in real time, and those tweets are consumed by the platform as and when they are happening. in all in real time, and then whatever operation you want to perform on with those tweaks, you are doing those operations, performing the operations all in real time. With Jet, you have the flexibility of basically, defining the flow of your application processing. What you see on the screen, what's on the next one? Right. Sorry, what happened? What you see on the screen, these small dots and these arrows, no, yeah, these dots represent processes. So you define the processing units or the compute units, basically, and each unit is basically a stage of your processing, execution. So you do each. If I go here, in this is an example where a transaction comes into the system or a data point comes in the system, and you have already defined 6 different stages that you want to perform on that data entry that has come in the system. So one of them would be ingestion, where you are ingesting the data. The next stage is transformation. The next stage is combining, which is where you run aggregation and analytics. And the next stage would be streaming, and the last stage would be publishing. So all these dots, they denote the stages, the processes. And all these arrows, these are the connectors. These are called edges. These dots are called vertices. So in the DAG language, there are vertices, which are basically the representation of processing or compute units. And there are edges. Edges are the connectors to your vertices. So as you can see, with DAG, one process or one compute unit is able to receive input from multiple compute units. So here in this example, this one here at the center is basically receiving input from this processing and this processing, which is basically here, you might be performing transformation on here, and you might be performing, let's say tokenization of your data and aggregation of the, running some calculation on the data. And then that aggregation is happening here on this compute unit. So, and one compute unit, one vertex is also able to emit or transmit data, its output into various compute units. So this guy here, this vertex here is able to send its output to this guy here and this guy here. Same goes with this one. This compute unit is able to transmit its output into here and here. So that's the kind of flexibility you get. That's the kind of control you get when you are defining a job in Jet. And it's all happening in the memory. Now, the way things run in a Jet cluster, you have pipeline and you have jobs. So what is a pipeline? Pipeline is basically your is a framework, is a programming framework, is the APIs that you use to define several stages of your job execution, all those stages that we just saw. And once you have created, or once you've defined a pipeline, then you submit that pipeline into the cluster as a job. So think of it this way. Those who are familiar with Java util concurrent APIs, in there you have executor service framework, where you create an executor service with a certain thread pool, and then you submit your runnables or callables to that executor service. And whichever thread is available, that thread takes your runnable or callable and executes it. So your executable, your runnable or your callable is basically your job, right? Is your pipeline, and your executor service is the tool that runs your job. Something similar happening here. So you define your pipeline, you define your stages using Hazelcast Jet APIs, and then you submit your pipeline as a job that runs on Hazelcast. Now, based on the task that you have defined in your pipeline, a job may run infinitely, where it is basically listening to a constantly flowing stream of data and processing it and publishing the output, and it never stops. Or a job may start, does something, does its job, does execution, on the data which is stored somewhere on your disk or somewhere in your file system, and then finishes it. So it is entirely up to you how you define a job. And then that job runs in parallel across all the cluster nodes. So you have a platform that has several nodes in the cluster. When you create a pipeline and submit a job, that job goes to the cluster and runs on all nodes in the cluster. This is how a pipeline looks like, just a crude example. And when I give you a demo, I'll give you the demo. I'll show you much more about what you can do with pipelines and what you can't. Just a crude example of pipeline. So this is an example of, basically a data tokenizer or a string tokenizer and aggregator. So here, the flow of the job execution is that you connect to a data source, which may be a file system. You read from it, then you perform some mapping operation, then you perform some filtering operation, and then you aggregate. So think of it as a word count use case where you're counting how many times a single word has appeared in a given text. So a data source might be the text, and then you perform mapping operation, you perform a filtering operation, then you perform aggregation, and then you publish the output. So this is how you define a pipeline, where using APIs, you draw from a particular source, then these are your mapping operation API, your filtering API, grouping aggregation API, and then your output API. So the platform as a whole, the combination of IMDG and JET is able to solve a lot of complex problems at in-memory speeds. Payment processing, fraud reduction, some of those we have seen already. Stream and batch processing, it is solving critical problems, at Sigma Stream, at Daegu Smart City, at British Gas, and so on. And it is solving a lot of artificial AI machine learning problems at Deutsche Bank and CGI and various different customers, and so on. I think there is no need of. Okay. Some of the key benefits that most of them I've already described, but just as a review, Hazelcast is an in-memory technology that uses the RAM, the memory of the system that you run on. The servers can be easily added or removed from the cluster to provide flexibility and to provide scale out, scaling in. The data model is not relational, so we're not talking about tables or stored procedures. We're talking about object-based data models. We support different types of languages: Java, C, C++, .NET, Python, Golang, and many more. And like I just showed you, it is highly resilient technology. It is able to deal with any faults and failures on its own automatically. Some of the other use cases, we work very closely with IBM, which is why you see IBM here. But edge computing, where Hazelcast is not just used at the backend system for running the heavy duty backend processing of your IoT data. It is also used in edge devices. So in modern applications, where in IoT use cases, so where IoT sensors are usually connected to a local edge device, and that edge device is usually connected to the backend system, where the data received from IoT devices is consolidated on the edge device, and then it is usually sent to the backend operation for backend operation. With Hazelcast being a highly lightweight technology, that it is so light that that it is only 14 or 15 megabytes of file. At times it becomes 20 megabytes depending on which version you're downloading, but not more than that. 20 megabytes of file, downloading it, a jar file, putting in a VM and running it as Java process, which only requires a few, less than 150 megabytes of heap space. That is a very tiny application, and just that aspect allows Hazelcast to be used on edge devices. So now today at Daegu Smart City in particular, edge devices are performing initial aggregation, and they are doing a lot of work with regards to the data, whether in a way that they are becoming smart that whether any data point needs to be sent for backend operation or not. So they are making those decisions at the front end level itself, and which makes the entire processing logic ultra fast. Let's skip this. Multi-cloud, I'll give you a demo very soon. On multi-demo side of things, like I mentioned earlier, Hazelcast is highly cloud native and cloud compatible technology. It is used natively with all these platforms, all these technologies that you see on the screen, be it Amazon EC2 or GCP or OpenShift Container Platform or Cloud Foundry, Kubernetes, Docker. It's there, right? Azure, so it's all natively compatible there. So when I say natively compatible, the example would be if you want to deploy Hazelcast, on Kubernetes cluster through Docker, just go to Docker Hub and download an image of Hazelcast. Right? Let me actually show you that. Docker Hub. Look for Hazelcast, and you have Hazelcast images there, the most recent versions, and and the archives. So that's how natively compatible Hazelcast is. It can be deployed in two different ways, client server mode as well as in embedded mode. Client server is the traditional way where you run Hazelcast servers in their own dedicated environment and let his applications connect to the cluster using their native APIs, the client APIs. We provide client libraries to different client languages, Java, .NET, C++, and all those things. And all these different client applications can interact with one single cluster at one time, at the same time using the same data without any problem. The other way of deploying Hazelcast is embedded mode, where you can run Hazelcast inside your Java application. So, give an example. Let's say
Hi, could you maximize the font size in case you want to explain anything?
yeah, I'm aware. One moment. Okay.
Yeah, that's fine. Thank you.
Yeah. All right. So let's say this is your app, some application, right? And you are performing certain operations here. Let's say int a equals to 1 or whatnot, and then you're performing certain operations here, right? Oops, too fast. And actually, it's a infinite loop. That's a bad example. Anyways, you get the gist. Some operation. And then you have a need to use Hazelcast, right? So here you define your configuration. Forget about this for a minute. All you need to do is Hazelcast instance, Hazelcast equals to Hazelcast dot and new Hazelcast instance, and that's it, right? At this point, you have turned your application, your simple Java application, into a Hazelcast application, right? So Hazelcast dot get map, right? Immediately you get reference to a map. Do this and map dot port or map dot get and whatnot, right? So you can perform the operations with Hazelcast data structure. So this, and then you run your more operations, right? So here you had an application which was doing something, and then you have Hazelcast, which is where you start using, Hazelcast data structures, and then and then you continue with the operation with the application. So this makes your standalone Java application and converts it into a Hazelcast server node. So your standalone Java application also becomes a Hazelcast application or Hazelcast cluster node. This is what is called embedded mode, and this is only possible in sorry with Java apps, because Hazelcast is a Java based technology, and it can only be used inside a Java application if you are using in embedded mode. And also a great tool to be used in microservices based architecture. Again, you can define different level of different isolation level in your microservice architecture, and Hazelcast can fit in all those different isolation levels quite easily. These are the different clients that are supported: Java, .NET, Python, Node.js, Clojure, Golang, and so on. And if you are keen, then you can actually visit hazelcast.org and so go to IMDG, and you see clients and languages. This is where you'll see all the clients which are supported and what the features that are supported. Right? This is where you see all the details. Um, Hey, Souvik, how are we doing on time?
You have almost another hour available, Rahul. It's a 2 hour meetup, but I kind of said that we do it for 60 to 65 minutes and do a demo and leave some time for questions. There are quite a few questions coming. So if you want, you can take a break for 5 minutes. I had a couple of announcements. So then we can take a break and then you can take a few
I
questions. How do you want to do it?
Let me quickly go through some of these key features, and then I will
Yeah,
pause before the demo.
sure. Thank you very much. Please go ahead.
Cool. So some of the key features that one can benefit from is the security suite, a very commonly used feature by almost all of our banking customers. And I don't need to mention, I don't need to talk about the reasons why it is important. Hazelcast Security provides the industry-grade end-to-end TLS SSL encryption, mutual authentication, JAS-based authentication and authorization-based access to your data, security interceptors, LDAP integration, and then there are certain compliances. So for example, FIPS, SOC 1, SOC 2, PCI, ISO 27001, all these are in place. Um, with Hazelcast Security, you can secure the entire ecosystem which uses Hazelcast. So all the way from your client to the server, if you're using Management Center, which is the Hazelcast UI tool, that and back to the client. So all those components of the Hazelcast ecosystem can be secured using Hazelcast security features, and you do not need to perform any. Sorry, you do not need to write any application code or anything. This is all configurable. So you basically put put the relevant configuration in, and you're good to go. WAN replication, it basically is the technology that allows you to run multiple Hazelcast clusters in different, maybe running in different location or in different data centers in different parts of the world, and keep those clusters in sync with each other. So, for example, here we have one cluster in London and one in Paris. They they exchange data with each other. So, if you have clients connected to both clusters, um, then whatever update that London cluster receives from your clients, they are replicated into Paris cluster and then vice versa. You have the option of defining the direction of the traffic between the two clusters. You can keep them two-way, which makes them active deployment, or you can keep them one-way, which makes them active and standby, one active and one standby, or call it one DR. so that you have updates going into one cluster from your client applications, and those updates are being replicated into your DR or standby cluster. And if primary your active cluster goes down, or if you shut it down, yourself, then Hazelcast has the flexibility or the tools, sorry, not tools, the features, these are called automatic disaster recovery and blue-green deployments, that allow your clients to switch over from one cluster to another automatically. So if your clients were connected to London cluster, and if London cluster goes down or does not become available for whatever reasons, then your client can detect it automatically and switch over to Paris cluster. Um, you can do that manually as well. So you can, if you wanted to perform a scheduled maintenance in London cluster, then what you can, but you did not want to affect the availability, then you can do is you can switch your clients manually over to Paris cluster before you shut down the London cluster, so that your applications do not incur any downtime. And then you can do whatever you want to do with the London cluster. Now, when you bring the cluster, when you are done with your operations or your maintenance with London cluster and you bring it back up, then of course it's not going to have any data, because the data was stored in the memory, it's a volatile space, and the data is gone. So before you switch your applications back over to London cluster, what you can do is you can manually copy the data from Paris cluster into London cluster, so that the data across both clusters remains consistent and is available for use by your applications, and then you can switch over your application. Another feature is called high density memory store, where it is a memory store outside of JVM heap, and this allows users to configure or to sorry to configure Hazelcast nodes with with higher amount or higher volume of with higher amount of memory store, so that they can store large volume of data without running into GC problems. So in this example here, all this orange strip is your memory space, is your RAM. In that, you can define that, okay, I have 100 GB of RAM available. What I'm going to do, I'm going to run my Hazelcast server process with 4 GB of heap, so that I don't run into long GC pauses. And then I'm going to use 90 GB of my RAM as high density memory store, so that I can store lots of data into one Hazelcast server node. Now, the advantage of using high density memory store is that it is created outside of JVM heap, although it is managed by the Hazelcast, the very same Hazelcast process, but it is created outside of heap. So, and since it's created outside of heap, it is not visible to the garbage collector. So the garbage collector does not have any business to do with the high density store. So there are absolutely no GC pauses with high density store. And Hazelcast has its own patented algorithm of handling memory fragmentation and defragmentation. There is one important thing that you see at the bottom of the screen, which is called Intel Optane. Optane is the latest offering by Intel. It's basically a persistent memory store. It's called Optane DC. Um, uh, so traditionally, when we use DRAM, it is called, which we basically call RAM, and it is a volatile space. So that means that nothing is stored or persisted in that in RAM, on RAM. So if you have an application or Java application which you use to store some data into, and you switch it off and you bring it back in, then the data is gone because the data was on RAM. With Intel Optane, you can enable persistence on the Optane DC. It's a different memory chip altogether, very cheap to use and cheap to purchase. And but different chipset altogether, and you replace your DRAM with your Optane DC memory, and you enable persistence, so that any data that you have stored on Hazelcast process is remains there in that in that memory space, so that when you bring it back up, the data is there, and you can it can read from the persistent store and hydrate its caches without having to reload the data and so on. The next bit is hot restart store. Hot restart store is a feature that allows you to persist your in-memory data into Hazelcast. That allows you to configure Hazelcast servers to persist their in-memory data into a store of their choice. So traditionally, sorry, not traditionally. I would say we recommend that to be SSDs because SSDs are faster, gives you good amount of performance compared to spinning disk. So you define a location to each Hazelcast server node, and when you enable hot restart store, the servers store their in-memory data into its own persistent store, so that when you shut down the cluster and you bring it back up, the servers are able to reload the caches or hydrate their caches from its hot restart store, and you don't have to manually load the data into the memory of the servers. This little table here is a bit outdated. I've been seeing this for more than 2 years now. So that means that the latest SSDs would be even faster. And what this table shows is basically the performance, the read throughput of data from hot restart store back into the memory space. So basically, in a 10 node cluster, 100 GB of data can be loaded in less than 10 seconds. So in one single node cluster, 100 GB of data can be loaded in 82 seconds. And thus, these are the crude numbers. With modern SSDs, it is bound to be even quicker. Now with Intel Optane, it is even faster, right? As you can see, with Intel Optane enabled, where the hot restart store lives on the memory in the RAM or in the Optane DC personal memory store, the speed of loading the data is way quicker. It's around 3 times faster than loading from SSDs. As you can see, 87 GB of data was loaded in 18 seconds. Rolling upgrades allows you to upgrade the versions of Hazelcast servers in a running cluster without having to shut down the cluster and affecting the availability. Another feature, downstream persistence, where I think I've mentioned this several times already, where when I said that Hazelcast servers or Hazelcast cluster lives happily on top of the databases, and then applications only interact with Hazelcast. They write into Hazelcast and they read from Hazelcast, and whatever they write into Hazelcast can be persisted into the database. This is just a visual representation of that analogy. So you have applications feeding into Hazelcast IMDG. You're performing map write operations, whether you're using map.put or map.set API. You're sending some data, which is in the form of key values. The data goes into Hazelcast IMDG. And then as soon as data comes into IMDG, into Hazelcast, it is sent downstream to a database. Now there you have two options. One is write through, which is a synchronous process, where when your applications write something to Hazelcast first tries to commit this into the database. So before the transaction is committed into Hazelcast store, it is first sent to the database for commit. Only when the database says that, okay, I'm happy, then Hazelcast stores in its own cache and then sends the acknowledgement back over to the application. In write behind mode, which is asynchronous mode, here Hazelcast stores the data in its cache first, and then it handles the DB persistence asynchronously behind the scenes. And then there is another option of running Hazelcast with database, which is when an application sends a request to read something from Hazelcast, and the data, let's say, is not found in the cluster, or the cluster is empty. You just started it and you did not have hot restart store enabled, so it's a plain vanilla cluster. Then read through is invoked when the data is not found, which basically means Hazelcast goes into the database, pulls the data, stores in the cache, and sends the data back to the application. And all this happens automatically behind the scenes for you. You don't have to do anything. You don't have to perform any manual operation apart from configuring or putting the right configuration at the start of the cluster. Skip this. Management Center is a UI tool of Hazelcast, gives you a full complete view of the cluster, but what all servers you're running, what all clients you're running, what all data structures you are using, how the data is distributed, the performance of your servers, your latency operations, your throughput statistics, heap usage, CPU usage, and all those things. And I'll give you a demo. When I give you a demo, I'll use Management Center, and you can see what that thing is all about. Okay, this is where I will, I will stop speaking. I'll shut up, and we can take up questions.
Sure. First question was there from Nagendra sir. That is, see, the people had there's like a questions from the Redis use case you shared about, I believe. Sorry, can't remember the customer's name. Where he said Redis was 3 times faster. Sorry, Hazelcast was 3 times faster compared to Redis. So the question they had was that Redis is also in memory DB. How is Hazelcast more efficient? Could you share in a bit more insights on the POCs and POVs you had run?
Absolutely. Simple. Redis is a single thread technology, where each Redis server node is a single thread server, whereas Hazelcast is a concurrent technology. Hazelcast creates as many threads. Sorry, the number of threads that Hazelcast creates to handle user operations is dependent on the number of CPU cores that are available in the underlying system. And then certain, the way Hazelcast IO works, the way, the protocols are written, and the way servers handle the data operations, read, write operations, delete operations, running queries, and so on. That's the whole package makes Hazelcast faster. Another aspect is that Redis is known to crumble under high data load. If you, and I'm not making it up, you can, this is something we have, heard from the customers, and Redis themselves, mentioned this on their documentation that, as soon as data load goes or reaches certain threshold, it stops replicating data from primary into its replicas in the shard, which basically means if primary goes down, then there is no way you will read the fresh copy of the data, because the shards, sorry, the replicas have not been updated with the primary data, because the data load was just too big for Redis to handle. And then they announce it publicly, so all there in public domain in the documentation as well. So yeah, I mean Redis, and there are lots of other capabilities that are not found in Redis, and in Hazelcast is there, with database sync up, WAN replication, and all those things that basically attract a lot of customers to Hazelcast. We have had a lot of customers who moved away from Redis to Hazelcast.
Okay. The next question was, you mentioned that Hazelcast is effectively an implementation of the concurrent hash map, right? You did mention it in one of earlier. So and it is, I understand it's completely written in Java. That's why the first deployment option where doing it in memory is only supported for the Java language. So and people are saying that Redis is also some kind of a key pair value, but I think you have explained why Hazelcast outperforms Redis in most cases. There was another question around the oil field use case. Okay, Anuj, I can correct me if I'm wrong. The question was that usually in oil fields use OPC based communication. I'm not sure what OPC is, so I'll be honest about it. So does Hazelcast behave like an OPC server? Anuj, if you would like to unmute yourself and explain what you mean by an OPC, just for the context, as well as Rahul's,
Yeah, sure, Savik. I work for an oil field company, Halliburton, and I do something very similar there. So what we do is we collect data from different PLC devices. It's like it is built by different companies. So to unite them, actually, we use something called as OPC, which is Open Platform Communication. And we just collect that data and then we send it to a singular cloud and something like that, and where we further process. So what we do is collect this data. OPCUS server is the one where we have it temporarily. It's almost like a RAM based system only. It is both stack based, so it's just where we get the data, and then probably we then push it to something like a Kafka stream or anything of sort to then process it on the server. That is more like to say some cloud like Azure or something like that, and where the data is then permanently stored into some database and then processed actually. So I want to know actually, does Hazelcast do something like OPC server where we hold the data in the edge device actually, and then for further then it is then sent to the server, something like that.
That's right. So you can Hazelcast, since it is so lightweight, it can easily be deployed. It is actually being deployed on edge devices. In some of the IoT use cases, things like I mentioned, Daegu Smart City projects and British Gas. The oil rig use case is not, is not much of an IoT use case. It is where Hazelcast runs on premise, right? Where the data is ingested, which is produced by those drill machines. Is yes, it does first initially go into an edge device, and from there it goes straight into Hazelcast. And the edge device and Hazelcast, they run both in the same parameter, the same premises. But to answer your question, absolutely, Hazelcast is deployed on edge devices, and because of its lightweight nature, and then it is also used in a larger capacity at the backend, for performing backend operations.
Thank you.
Okay. Thank you. Okay, there was another question from Praveen, I think, which is an interesting one, that you mentioned about the pipelines and jobs. So the question is that can the pipeline be updated during processing? So like you've submitted the pipeline to the job, but you want to do a change. How does Hazelcast handle like replacing an edge or adding new stages, something like those on the inside?
So you can change a job definition of a job which is already submitted and running in the cluster, and then resubmit it. And the way it works is, it basically, when you have that feature enabled, then Hazelcast persists the various stages of job execution in the form of checkpoints. So whenever job definition is updated, the execution is picked up from the last checkpoint stage. But it's just not. But don't hold me onto that, because there is much more to updating the job definition running cluster. What I would advise is that if you go to, can I share my screen again?
Yeah, sure.
If you go to Jet documentation, there you will see job management, submitting jobs, auto scaling, suspending, resuming, restarting. No, not that. It's here. It's here. Somewhere here. Updating jobs. It's basically a commercial feature. It's not open source, but here you can update the pipeline. And like I said, it basically picks up the execution from the last stored checkpoint, which is called a snapshot, and then it continues. So yes, to answer your question, it is very much possible. You can find more information here.
I have shared the link with the audience so they can have a look at it. Okay, there's a question for Amita, which is how does Hazelcast refresh the static data loaded from DB? Basically, how does when the data changes, like refreshing your cache, how does Hazelcast do that?
Sorry, what's the question again?
The question is that if you have added more data into your data store and that needs to be reloaded into the Hazelcast cache, how does it do it?
If you have loaded data into the data store outside of Hazelcast?
Yes.
Right. So there we have various offerings in the form of CDC based, architecture. I don't know if you know about CDC, change data capture, where our CDC plugins, they run They connect with Hazelcast on one end and the database on the other end. So any update that goes into the database, those updates are basically captured by the CDC plugin and sent immediately into Hazelcast, so that you don't have to manually update the cluster with the updates going into the database.
Okay, thank you. There are a couple of questions from Sanjay in that he was referring to the embedded mode of deploying Hazelcast. So in the embedded mode, how does Hazelcast discover other JVM services? That's the question.
That standard way of discovering as you would use in client server mode. So basically, either running in TCP/IP networking, where you define IP addresses explicitly, or running multicast, or running any other discovery. If you're running, for example, if you're running on Amazon EC2, then you deploy your application instance on EC2 VM, and then if you are using as a task in the application instance, you basically use the EC2 discovery module. It's a standard discovery for Hazelcast, whether it is embedded or client server.
Okay, and he's referring to particularly something called as Eureka service. So I believe that's a ETCD service. Or Sanjay, if you can unmute yourself and elaborate
Yeah,
what is
Eureka
Eureka.
is also supported.
Okay,
Let
great.
me go back. Yeah. So Eureka, Console, ATCD, they're all supported.
Okay, yeah, thank you. I will have a couple more questions and then I'll probably let you do the demo and then we can take the remaining at the end. So
Okay.
there was a question that the Hazelcast can interface with multiple databases to extract data and keep it in memory. So is there has there been a use case where you tell that, okay, this type of data or data from this source should go into this location? Because that's a question which is coming from Suman, that how could you clarify how the client indicates which data goes where kind of situation?
Sorry, I lost you the
Yeah,
question.
sorry. What I said was that Hazelcast can consume data from many data sources, as you mentioned. So if there is there a business case that you kind of partition the data within the memory that, okay, data from this source is in this location, data from this source is in this location. Is there a
Yeah.
business case for it, and is it achievable?
Okay, it is not for you to worry about how the data is segregated, but yes, the data is partitioned, whether you are using caching or computing, the data is always partitioned, and whatever data that you are receiving, let's say from a stream into the system, that data is processed by the job which is listening to that stream. So not, you may have thousands of different jobs running in your cluster on the platform, and but not all the jobs are listening to the same data source. Each job, if you remember, one of the stages of a job or the pipeline was to define the source or ingest. Now that ingestion is basically defining the source where that job will receive its input from, and that's where you may have different types of sources supplying or feeding data into one platform, and that data is consumed by its relevant job. But
Okay, I think I got the question from Sumant, Rahul. I'm sorry. It's like, what it means is, I believe in the pipeline, you can both define both the input and the output. So you're ingesting it from one location, and as a part of the sync, you define that it goes into this location. I think I remember seeing the code. You had both the options. The
yep,
destination as well as source could be defined as a part of
yep,
the pipeline. I remember
yep,
in the sample. So I hope
yep.
Sumant that answers your question. There is, it's an option clearly defined in the pipeline. I remember it now. Yes. Yeah. Drain to.
Yeah, the API might have changed in the latest version. This is
Okay.
again an
Yeah, but
old
you
version.
can define both the data source and
So
the
you
data sync.
the draw from is basically where you define where the job will ingest or consume the data from, which is where you're defining the source. And here the source is just a standalone Java map. And the drain to is where you will publish your output to. It's basically your sink. So this is your source, this is your sink. And I think if you see the API the default API, the connectors, it actually uses sinks. And the latest API would have changed
Yeah. Okay. Fine. I think that I'll stop the questions for now. Can continue the demo, Rahul, and then we have maybe a couple more questions, unless there's something from the demo.
Okay, cool. So one question from me, what is the demo?
You can
Uh,
choose for us as well as for yourself.
no, I'm just uh, no, just kidding. Okay. Hmm. So the demo, today's demo is going to be based on the payment system, payment processing, and something similar to the fraud detection use case. And um, I'm just thinking as to where can I find. Okay. I'll come to that in a second. So this payment processing use case is basically a simple case study where you generate a transaction, whether you swipe your credit card or you are performing an online bank transfer, or you have purchased something online and you want to keyed in your credit card number and that needs to be processed. So in a typical payment transaction processing, there are several things that happen, and the two key stages of a payment processing are basically authentication and fraud detection, where you authorize whether the transaction is genuine, whether there is enough balance in the account, and so on, and then you run, other various fraud detection checks that that the transaction is coming from a genuine source, a genuine owner of that payment device, a payment device holder. Because what may happen, if you swipe a credit card in London and an hour later your credit card was swiped in New York, then it is literally not possible, right? And that's a fraudulent transaction. So somebody might have scammed your credit card already and then is using all over the world. So those are the things that take place in fraud detection. And again, that was just a crude representation of the entire process, because in fraud detection there are thousands of business rules that run during the fraud detection and authorization process. um, Some of the common payment systems that you would see that use these fraud detection and authorization checks are basically core banking, or ATM, internet mobile, corporate banking, and so on. Um, some of the key challenges when you are designing an infrastructure for such use cases are basically stringent SLAs with respect to authorization on a transaction. When you swipe your card on a terminal, you typically get a response back within 2 or 3 seconds. But keep in mind that major part of those 2 3 seconds is spent in the network, right? The transaction has to leave your terminal, go and has to reach your backend system, and then from backend system it has to reach the system which is running your fraud detection and authorization checks and all those thousand business rules, and then the result has to be produced, sent to the backend system, and come back into your terminal. All those things need to happen within 2 or 3 seconds, and we know that, we have seen that, right? We do this day in day out. um, so it leaves us with very little time. So the requirement is to basically build an infrastructure which is extremely fast, which can create a response after running all those validations and fraud rules in less than a second. Some of the customers, the likes of Standard Chartered and Visa, they have even stringent requirements, and they want to run everything. They want everything done in less than 100 milliseconds and so on. And then another requirement is to deal with massive transaction volumes. Some large customers like Apple on a Target on Black Friday, or Apple on any new product launch, they have millions of users worldwide logging into the system, so that and then all those users need to be served, without any interruptions or downtime. Um, and same goes with credit card and the payment transaction systems. The likes of customers, the scale of Standard Chartered and Visa and Mastercard, they have hundreds of millions of POS devices, distributed across the globe, and tens of millions of them, they are always active all the time, which basically means their systems are churning data, producing data, and their machines are running and running these algorithms and fraud checks all the time. 24/7 availability is paramount. So this was now the solution architecture that I'm going to show you is basically from one of our customers. I cannot take their name if I have not already put their name on this slide by mistake. Yes. So I cannot take their name for the reasons obvious, but a standard payment processing use case where a payment transaction when it goes to the backend system, the mainframe system in this case in particular, for processing the mainframe the mainframe application puts a transaction onto a Kafka topic, Kafka event bus. That Kafka brings that transaction into the Hazelcast system where they have different microservices running all together, and as soon as the transaction comes into the system, it is picked up by first microservice, and which is basically whose task is to transform the transaction, and then there are other several microservices running in parallel, and so the transaction has to go through all these microservices, and then once the output is produced, the output is dispatched back onto Kafka, and which is basically taken back onto the backend system. And all these microservices, they run on Hazelcast. They use Hazelcast for caching purposes. They store data, intermediate data, which is data basically updated stage of each of the transaction by each microservice stored in Hazelcast. And then after the transaction is completed, the transaction is stored in DataSets Cassandra, which is the underlying database, for 30 minutes or so. And then it is cleared from the database as well. So this is the end-to-end architecture of one payment processing use case. All these fraud checks, so this particular use case has around 3,800 fraud detection rules, which are executed in this processor microservice, and the whole end-to-end system is executed in less than 100 milliseconds. So right from the transaction arriving into the system and leaving the system is executed less than 100 milliseconds. This is what is another diagram of what I just mentioned. That architecture is deployed across multiple geographies through WAN replication, hundreds of GBs of data stored in each of the clusters, and there are multiple data clusters deployed across multiple zones for each use case for each market. All right, demo time. So in my demo, what I'm going to do is I'm going to show you a simple application of fraud detection, and where basically I will show a simple process of how Hazelcast platform as a whole pulls the data. Actually, you know what? Let me show you this slide. Sorry, wrong one. So this demo, the requirement was to provide ultra low latency access to the data and ultra fast computation of the data of the transaction that is produced into the system, and also when we're using WAN application, it was basically to externalize the data and make it available to other applications. When I say externalize, what that means. So here is what this demo is going to do, which I'm going to show you in a minute. So this is not the demo. This is just the overview of what the demo does. Right. So don't just leave the session today, because this is the starting. So in this demo, we have an on-prem cluster which will run on my laptop, which has a MySQL database. It also has I'm going to deploy a Hazelcast cluster, and it also has an application which basically receives a transaction. And then there will be a cluster deployed on AWS, same Hazelcast cluster, which will be receiving data from this guy on-prem cluster. So what happens is Hazelcast platform will load the reference data or the static data or call it historic data from MySQL database into its memory, into its cache, so that that data is used for transaction processing later. And as soon as the data is loaded into the on-prem platform, it is replicated immediately onto the AWS cluster, which you would have seen in the animation just a few seconds ago. And when a transaction is generated by the end user, it comes into the transaction system on-prem cluster, which basically sends the transaction, to Hazelcast platform. And when the platform receives the transaction, it performs its fraud checks and business rules. This is what it is doing. And the result is produced, is sent back to the receiver, which sends the result all the way to the original source of the transaction. And it also publishes the result onto the cluster running on AWS EC2. There, you can use that data for further use for for displaying on dashboards, create reports, or storing in database and whatnot. So now the real deal. So I have two clusters running, two node clusters running on AWS.
Rahul, could you just slightly magnify the screen? Maybe a couple more points. Yeah, that's fine. Thank you.
This must be clearly visible to you guys, right?
I'll take in feedback from the audience.
No, joking. All right. So hold on. Is this better?
Yeah, it's better. No, this went down, but yeah, now it's better. Yeah. Anyone from audience, if there are any question, any feedback, if it's fine for them, because it's all for the community. Yeah, that's perfect now. Thank you.
All right. So what I have is I have this instance running on Amazon EC2, and so is this guy. We have Hazelcast deployed and ready to go. So I'll start a Hazelcast instance there. It's coming up, and I'll start another Hazelcast instance here. Coming up. We can see this was the first member. And as soon as the other guy joins, it will be updated. There you go. The member list has been updated to 2 members. So member means one server node in the cluster. This is my node in the cluster. So this has got 2 members here. And I can see this. What I'm going to do is I'm going to start Management Center. Management Center is basically a tool that you can download from Hazelcast website, which is go to hazelcast.org, go to IMDG, download, and Management Center. And there you can download the Management Center. It is an enterprise tool. It works fine for 2 nodes, but anything beyond 2 nodes, you need a license. So, but I don't need a license for obvious reasons. All right. So what I'm going to do is start Management Server instance. And it will be started on my local host. It doesn't have to run on local host. You can run Management Center anywhere in the world you want. Your cluster may be running, in different part of the world, and you just need the accessibility for Management Center to your cluster. So what I'm going to do is open up a browser, localhost 8080.
Rahul, is there a configuration fed into the Management Center which talks about the nodes to go and talk to or automatically?
Yeah. Hold on. Coming to that. So I've already created a user, which is why I didn't have to create one. But when you start Management Center for the first time, it will ask you to create user and password and then so on. So once you've done that, go to Manage Clusters. Here I will.
Okay.
So when you start Management Center, this is what you get, right? If you have nothing, starting with the first from scratch, this is what you get. So we go to Manage Clusters. Here, I'm going to add the cluster configuration here, where I'm going to add the name of the cluster, which is EC2, and I'm going to provide the member address, which is the address of my EC2 instance, which is ignore these exceptions because it is not able to find the server node which it previously defined. So what I'm going to do, I'm going to pick up this.
I'm
this
making you
address.
work extra hard for the demo. Sorry for that.
Sorry?
I'm making you work extra hard for to show the everything.
No,
As
don't
in you
worry
had
about
added
it.
it.
Don't worry. No. It's all right. Don't worry. All I've done is add it, and we'll just wait for the green light. It is trying to connect. As you can see, the cluster has received the connection request from management center here. There you go. I've got a green light here, EC2. I select this, and there it is. So I have two members in my cluster, which is shown on the management center console. It shows one client. The client is basically the management center. The management center, when it connects to the cluster, it connects as a client. So don't worry about when you see a client, and don't get spooked if you have not run any client just yet, because it's just the management center instance. Members, two members, we can go into each member and we can see different type of statistics, CPU and memory usage, native memory usage. We can see the underlying resources configuration, the system configuration. We can see the member configuration, Hazelcast XML, and all those things. I can shut down the member from here. I can take thread dumps of this member, copy and paste, and all those things. I can enforce system.gc from here, although it's not going to do much because I don't have anything here. And that's it, right? So here I do not have any data structure because I have not created anything, right? So it is all running on EC2, and these are two members, and this is my cluster up and running, right? Now, what I'm going to do, go back to my application where I am going to now. So remember this. So this is my EC2 cluster, right? Now I'm going to fire up the on-prem cluster. So here, don't need you, go. Sorry.
Yeah, please take your time.
Yeah, this is an application that I wrote for the payment processing use case, where what it does, it basically, where is the public static void? Yeah, there it is, right? In this main, all I've done is basically creating a pipeline, right? In that pipeline, I first put in some of the configuration where I say I define my network configuration here. And I also define my map configurations here. So in the map configurations, I have two maps. One is account map and the one is merchant map. And these map, when I start the cluster, they load the data from the database. So I have a MySQL database. I do not know how I can, there you go. But I don't know how will I be able to do this.
It's
So
fine.
I have around,
We'll believe that it's proper data. So let's leave that there.
yeah. Hold on. So this is, let's start from account. So there are 2000 rows, or what we can do is, I have 2000 entries in the account table already, and I should have some data which I do not know how much. I think 151. Ooh, what is this?
It doesn't play well if you don't give a semicolon at the end of the statement. That's why.
And I have 151 records in the merchant table. Okay. Now this is pre-existing data. So in account table, I have 2000 customers already up, loaded, created and loaded, which basically means 2000 unique IDs. So 2000 unique credit card numbers, and they are from different merchants. So these 2000 numbers are from those 151 merchants that I've created. Merchants like Standard Chartered or SBI or HDFC and so on. Right. So when I start the cluster, this cluster is going to create two maps. account and merchant, and it will load the data from this MySQL database into its own into these maps, right? And then there is yet another map called rules result, which is used for storing the result of each transaction processing. Okay, and that's it. So what I'll do is I'll basically start this instance. Before that, yeah, I'll come to the pipeline in a minute. Right, this is where I build the pipeline. Call the pipeline in a minute. But let me quickly start the servers on the cluster. And I will just maximize the screen in a minute. Now I'll start another node. So I have 2 node clusters here. Okay. Here, where is it? As you can see, when the cluster started, it loaded all the rows in the merchant table, 151 keys. And same thing happened on the account the account map. It pulled 2000 rows from the account table and loaded into the account map. Now, to see this, and I'll come to this in a minute as to what these things are. But let's go back to the management center and connect our management center to my on-prem cluster, for which my cluster name is dev. I know that because I created it. And it's running on localhost. That's all I need. And I immediately connected. It's green light. Here, 2 members. They have some data, some graphs and charts, beautiful looking. Now I have 3 maps already, right? Why 3 maps? One account map, which has 2000 entries. As you can see, 2000 entries stored across the 2 maps, the 2 nodes in the cluster, and then there is backup also. And in the merchant map, I have 151 entries, which are spread. Oh, what is this? Sorry, wrong map. Merchant map, 151 entries spread across 2 nodes in the cluster, and so is the backup. Rules map has nothing. It should not have anything. I would be worried if there was something, because it is just used to store the rules of, sorry, the result of my fraud execution or the payment processing transaction execution. Cluster license expires in 26 days. I know that. Don't bother about copying this license because it's going to expire anyway. So, all right. Now, what we'll do is we have a job already running in the cluster. Here, I have a job which is called fraud detection job. I click, and these are the several stages of the job. So one is transaction queue, then there are this, and then mapping and queuing. So what this does, let's go to the pipeline and see what the pipeline is. So this is my pipeline. I initiated my cluster and I build the pipeline. And I build the pipeline. Here is my pipeline looks like. In here, I create several stages, right? The first stage, I read from a queue. So here, what I'm going to do is in this demo, I'm going to create a dummy client application, which will basically mimic creating a transaction or credit card transaction, and it will place the transaction into a Hazelcast queue into the cluster, and then the job will read from that queue. So instead of reading from Kafka topic straight away, I am placing the transaction into a queue, and the job will read from that queue, which is what you see here, a transaction queue, which is where the job reads the data from, and you'll see these some numbers very soon here. And then I perform certain transformation operation. So I receive the value from my dummy client, and then I'm going to perform some certain transformation on this. And the transformation entails transforming the REST value into certain things and then apply certain logic and basically creating a transaction object, a Java transaction object, right? Oh, oh, okay. Anyways, here. So after the transaction has been, sorry, after the transformation has been done, completed, I move on to the next stage. The next stage is performing the mapping operation on the transaction object that I have just received. So what I have done is I received a transaction from a queue and I transformed it and made a Java. So if you check, I receive a transaction in REST value, in this form of REST value, which is basically the, so what I'm doing is I'm submitting a transaction, making a Java object of REST value and submitting it to the queue. So my first task is to transform it from REST value into a transaction object. And the transaction object is basically, move away, is the transaction object which contains the details of the transaction. So the transaction ID, account number, it is associated to merchant ID, amount, and blah, 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 blah. All these details will be connected, will be associated with that transaction object. So what I do is I transform the data. Now, the next step is I am basically applying merchant rules on this transaction. This is my rule execution, my business execution, my fraud execution, which is happening here. So merchant rules is basically, I see that, okay, this transaction was processed at a Reliance store and this transaction is worth 50,000 Indian rupees, right? Now, what has been the traditional or the average transaction amount at Reliance store? Is it 5,000 rupees? Is it 6,000 rupees? For this particular account ID. If it has been the case, then why this transaction is doing from 6,000 to 50,000? It looks fishy. So that's a red flag, right? So that's the kind of logic is happening here. So if I go to apply merchant rules, this is where I'm applying, going into merchant rule engine and applying the business logic there. Somehow my links are not working, whatever, anyways. And then the next one is once I have received the result of the merchant transaction, merchant rules, then I apply the typical fraud detection historical rules, which is basically apply historical transaction rules, and I have a rule engine there which does its job. And then everything is done. My output has been created. I'm going to basically write this output into two things. One is result map, and the other one will be a queue sync. So I should have two data structures here. Yeah. So I have one map, rules result, and I have another queue, which is transaction queue. This is also used to store the result of the transaction that I've just processed. And this was done for another customer demo for some other purposes, but the idea was to show how Jet can write one output to various different channels. So now my next job is I have two servers up and running. Going into the management center console, go to job definition. My job is running, my data is partitioned. My transaction comes into the system here and it does certain things. As you can see, apply merchant rules, apply historical rules, and then it is basically writing the output to a map sync and also to a queue sync. I should basically make it smaller so that not much difference, but that's it. So now I'm going to fire up my dummy client, which will basically create 100 transactions and send it across to the on-prem cluster. That's my client. don't bother about reading it. Basically here I'm creating certain dummy transactions and I'm sending it to the cluster. I'll fire it up. So if you notice, it connected, this client connected to the two members, on-prem members on my laptop, and it submitted its the transactions, the 100 transactions that are created to the cluster, where it was these transactions were consumed by the job, the production job which was running there. Right? It has, as you can see, it has various dummy account IDs and amounts and merchant IDs and so on. Now let's go into the cluster. Actually, I don't think I'm create. Yeah, as you can see, this job, this instance receives certain number of transactions and so on. So if I go into the Management Center console, you can see total items flowed into the cluster on this particular production job 100, totals out 200. Total out 200 is basically because I'm writing into two things. So if I check this here, these are the various parameters, all time 100 in, 200 out. I was a bit late in showing the transaction, but you can see items in, item processed, item sent out. Same thing here, same thing here. And in the process queue, there would not be anything, 100 items were received in the queue. Now, if I go into the maps, aha, but before that, let me go to account map and see what are these things. So these are my get operations on this particular member, right? And if I go on to the member wide, so this member had these many get operations, and the other member had these many get operations, all other write operations, and so on. And if I go into the maps, I'll see there were rules being, sorry, the rule result map, which is being populated for 100 entries. So this contains the result of all the 100 transactions that were sent into the cluster for processing. Some of them were approved, some of them were rejected, right? So this was all happening in my on-prem cluster. But what was happening on my EC2 cluster? We forgot about it. So we go to EC2 cluster. Actually, I should have shown this earlier that EC2 had received the data in the account map and the merchant map as soon as the data was populated in the on-prem cluster. Why is it only 106 entries and not 151? Something went wrong. Connectivity issues. I'll look into that. But the rules result has all the 100 entries replicated into this. So the data was immediately replicated from on-prem cluster onto EC2 cluster as the results were being produced. Here. So the raw data, which was the reference data, which was pulled in from MySQL, was sent into platform, on EC2, and so was the result, which was also sent into the EC2 cluster. So we have seen that one platform is able to, do various things. It can cache data, pull data from the data, it can interact with the database, it can store data in its caches, it can do the processing, the execution, it can run complex business algorithm, and it can also replicate, externalize the data by replicating the data to a cluster running outside of the infrastructure somewhere else, in the cloud in this case. So hybrid cloud deployment, one single platform does caching and computing. That's demo.
Thank you, Rahul. Unless you had anything else to say. Okay, I know we've overshot it by 5 minutes so far, but
Yeah.
I'll quickly. Okay, I just had one question. First of all, the pipeline which you displayed visually, was that created from the code? Because I don't remember you creating it.
No. So again, sharing my screen. One moment.
What is it automatically created from the code? That I'm just I don't might sound.
So, yeah. So this thing, when the cluster starts, Management Center basically shows that pipeline
Yeah, it kind of goes, it finds that job and pipeline. Okay.
automatically. So whatever
Okay.
job,
Automatically. Yeah.
those are shown here automatically. This is built
So,
automatically.
yeah, so basically it's been all management is automatically visualizing the entire flow of your pipeline based on whatever written in the code.
Absolutely.
Great. Yeah, I think I just wanted to clarify that for the audience. Okay. I will. That was
Give me,
one thing.
give me a minute. Give me a minute. My wife is calling me. Just give me one
Yeah,
moment,
yeah, sure,
please.
sure, sure. Please take your time.
Yeah. And in the meanwhile, you can take the questions if you want.
Yeah, yeah. I was looking. I'll wait for you to give me a green card once you're ready to talk. There was a couple of interesting questions. Uh, a lot of them are actually about a kind of a comparison level things. I'll come to that a bit later. Uh, there was an interesting question from Sanjay, which is that in case the application is written in Java and it has extra RAM for caching, then embedded mode would be actually a great way of using Hazelcast for low latency applications.
I'm
I
here.
think,
I'm
yeah.
back.
Are you here? Are you back, Rahul?
Yes.
Yeah. So, okay, the question from Sanjay that in case you have, what do you say, application is a Java application and has extra RAM available for caching, then the embedded mode of deployment of Hazelcast would be best suited for low latency applications. Is that a correct understanding?
Not always. Keep in mind that data is distributed. So, in embedded mode, you know, the only data which will be local to your application process will be, first of all, if you're running processing, you do not have any control and you do not know where the processing is being executed. Right? It is executed on all the nodes in the cluster, but which node ends up needing what type of data and where the data is stored. The data might be stored on the machine where application has invoked the execution, or on other nodes in the cluster. So, but if you're asking from a purely caching point of view, then only amount of data which is stored in your node where the application is running, that is the only data which is local to your
Correct.
locally available
Yes.
to you, and that
Yes.
is the only advantage you get. So let's say in a 3 node cluster, only 1/3 of data is local to you. So that is the only advantage. But for the rest 2/3 of the data, you are anyways going to make network hops to the other nodes and get the data from those nodes.
Yeah, sure. Acha, I had one request from the audience. You remember you had shown the architecture for the demo in one of the slides. That was slide number 78. Could you just share that slide for a minute? Uh, I know there's no sensitive information in that. Yeah, just check it once and let us know. Where you had shown the processing of the data. I think he said slide number 78. I think, yeah, this one. And I think the previous one, the one before this. Oh yeah, this one. Yeah, this is 78. Yeah, this is 78. Yeah. So this is
Yeah,
the next one. Yeah, 78. If you could go back there, Rahul. This is 70.
yeah,
Yeah. Yeah. I hope that answers your question. I'm sorry, I couldn't remember the name. Okay, I don't have a name for the individual. Yeah, great. Thank you. Rahul, there's one question you mentioned that sometime in the future, maybe 6 months later, you're going to have a
mhm,
single Hazelcast platform
that's right.
where you can use anything from it. So is that being, I mean, how is that distributable available to the end audience? Is it the same Hazelcast jar or it'll change in some way?
It will be too early for me to say.
Okay, fine,
To
fine. I just, this is more of curiosity for me on my end.
Yeah, no, look, it is still in flux, still being developed, but it will be we are working with the objective of making it one single jar file, which will provide both capabilities. Whether it takes that shape or some other shape is something to be seen. I would say we are waiting. We're targeting Q3 later this year, September October timeframe.
No, no, it's
Uh,
fine. I'm happy for not you not to go on this. But at the moment, just to clarify the audience that at the moment, IMDG and JET are available as separate distributables to be used
correct,
for individual capabilities. Yeah, that's fine.
correct.
Perfectly right. Okay. The next set of questions are more like
But
comparison level questions. So I will,
but if you
yeah. Okay,
deploy
sorry.
that cluster, you can easily use IMDG data structures because all IMDG data structures are available in Jet cluster, which is what my demo application uses. My demo application deploys a Jet cluster, and internally it creates IMDG data structure. So if you can see, I use Jet cluster, I deploy a
Mhm.
Jet instance, not an IMDG Hazelcast instance, but internally I use IMDG maps or IMDG data
Mhm.
structure, right?
Okay. Yeah. Great. Uh, there's a question from Shrikant, which is that has some experience with Kafka, and
Mhm.
Kafka is more easily scalable. So if we use Hazelcast for simple caching in Java applications, how can Hazelcast perform better than Kafka? I'm not sure exactly how it's a very relevant question because
Uh,
it's like apples
they
and
are
oranges.
they are not related. Kafka is messaging. Kafka works well with Hazelcast. Kafka is messaging. Hazelcast is caching and computing. However, Kafka has an offering called Kafka Streams, which is basically the compute API of the data that is carried into by Kafka topics. But the problem with Kafka Streams is it works primarily with Kafka tools, Kafka topic in this case, and it works off persistent database or data store because everything with Kafka has to be persisted somewhere. So even Kafka Streams, when it comes in the action, it basically reads the data from a disk-bound data store, which is Kafka.
Okay, great. Is Hazelcast's roadmap publicly shared anywhere, which people can look at it
Uh, Good question.
as in new features which are being,
Yeah.
evaluated?
No, I understand. Good question. It is not,
Fine,
but
that's okay.
can do is I like the idea and I can see the significance. What you can do is talk to join our Gitter channel. There's
Okay.
a Gitter channel where you can interact with Hazelcast engineering and product management directly. And if you have any curiosity about what we have in the roadmap and so on, then you can ask those questions. But I think I should talk to my product manager and do something about it, whether we can publish some bits of our roadmap or important bits of our roadmap for in public domain.
Yeah, there was again a kind of a comparison question of Apache Ignite and Grid Gain v Hazelcast. Any comments? I previously trying people trying to understand if there are specific places where
Yeah,
Hazelcast.
look, if you there are a lot of differences. Performance-wise, the class is fastest the data grid in the market, and there are a whole lot of differences in the performance. We have compute APIs, Jet, and all those things. GridGen doesn't, and our off-heap memory, HD memory offering is far superior than GridGen's. Um, I would suggest is go to hazelcast.com and there's a this place called resources, and there you can find out all the comparative information against Redis or Ignite or Gemfire or Coherence and others. It's all in public domain. We don't hide anything. We do regular benchmarks, performance benchmarks, and we publish reports in public domain. It's all there. You know.
Okay, there are a couple of questions on the way data is stored in Hazelcast. So you mentioned that Hazelcast stores data and partitioning it into nodes. So what is the logic used to partition the data, and is it customizable? Like, can you define it?
No, the logic used is simple. Is the logic of consistent hashing, where when we store something, we take the key, serialize into a byte array, take the string representation of that byte array, and do a modulo by take the hash code of the string and then do a modulo by the partition count. You can change the partition count based on the amount of data you want to store in the cluster, but you cannot change that logic.
But the default count is 270 when I remember in a slide.
Correct. Correct.
So
Default
that
is
can
two.
be increased if required, you're saying.
Yes, it can be increased if you have lots of data to store. Reduce it if
Okay.
you have if the data size is